Yeah,
Is
is that
about 5
Mira?
minutes. That's right.
Yeah,
MER.
Yeah,
Yeah, it's fine. You don't
Okay,
have to.
yeah, I don't know anything
Yeah,
about
but I
that, so I'm
think
interested
I don't
to
know what
see
happened.
what that is,
Something in
yeah.
his brain
Really,
just sort of
But
said something
research
can't
going
get worse.
well? Yeah, it's
I
going
think
well.
he's too scared of.
Yeah, except I have
Like, he needs
a
to-
lot of exams coming out.
He needs
so
to
when they
like
turn off
exert
today,
power
he does
over his
two
school.
exams.
Well, classes are easy.
Yeah, the classes will be fun.
Okay,
Yeah.
this late in this.
Oh, I don't know.
It's pretty interesting.
Yeah,
Okay.
find out midterm from last week to this week.
Okay,
Yeah,
gotcha. Oh, that makes, okay,
yeah,
yeah,
yeah, I got some work to do.
okay. Well, it's gonna go. It's gonna-
Yeah, thanks. Yeah.
Yeah.
Even though this are
Yeah.
2 minutes late,
Good.
you
She's
can-
girl.
Wow, Mike sitting all the way. Oh, he didn't hear me. Oh, yeah, but
Maybe long.
nice sweater. I like your sweater. It's finally getting to the temperature where we can wear sweaters.
Yeah,
I've
yeah.
been wearing more this year, so, yeah.
So before we start the nuclear theory seminar this week, I would like to highlight the experiments at FRIF that's running this week. It's done at the RIA-6 facility. It is on the copper 59 P alpha knockout reaction. And the detector used is called music. It's an active target detector. And this reaction, copper 19 P alpha, is very important for type 1 X-ray bursts. If you have any additional questions, you can ask them to Melina Avila, who is the spokesperson of that experiment. Okay, so I'll share this now. And right. And it is my pleasure to introduce Weijie, who is a postdoc at Iowa State University. He did his PhD at Iowa State as well with the group of James Berry. He used an ultrasound model for factor calculations and studied chiral potentials. And currently is an expert on quantum information applied to many body calculations in nuclear physics. Okay, this Weijie, you can take it away.
Can you remove the
Yes.
So nice to see you, folks. And today my topic is nuclear many-body structure and dynamics on quantum computers. Can the last row hear me clearly? Oh, okay. So as introduced by Dr. Grigo, my name is Weijie Du. I'm from Iowa State University. And yeah, it's my pleasure to let's say to have a chance to give this presentation to introduce my work here. And I will also thank you all for your interest in my work. In our work, actually, these are my collaborators. James Berry was my supervisor, and Professor Xingbo Zhao, he is a great helper to me, and Dr. Andrei Shirokov, he is an active collaborator with me on nuclear reaction theory. And Dr. Malun Sheriff, he's now moving to China for a postdoc appointment. And we are working together on in developing nuclear theory. And Dr. Chao Yang and Mr. Li Liu, we are working together on quantum computing. And these are the two students I supervised actually on some quantum computing projects. And today I'm going to introduce some basic knowledge of quantum computing and its application in many-body structure and reaction, structure and dynamics theory. There's a great grand challenge in nuclear physics, that is to describe nuclear physics at all scales based on the most fundamental degrees of freedom. However, if we would like to do that, and based on the first principle applications, approaches, we would face direct difficulties. That is exponential growth in the number of states of the quantum many-body system when the particle number grows. Yeah, this is a challenge, and this is the difficulty we face. And surely, I mean, there are sweet spots for ab initio calculation of the nuclear many-body and many-nuclear structure and reaction theory. For example, people could study from first principle the structure of nuclei, and also we can study dynamics of the nuclear reactions. However, I mean, as I said, there are exponential scaling in computational resources for many-body problem. For example, you can see from this direct plot, these are let's say up-to-date FCI calculation for the nuclear isotopes, for structure calculation of nuclear isotopes. The x-axis scales the number of particle bases, and the y scale stands for the logarithm of the matrix dimension. And we see that the current FCI limit stands at 10 to 11th. However, for example, if we would like to get the carbon 12 calculated, we would immediately, let's say, exceed this let's say our current limit of the computation resource. Therefore, you all recognize this space, right? It's Dr. Feynman. It says that let's make a new computer because nature is quantum mechanical. Therefore, we need to make a quantum mechanical computer. That is so-called quantum computer. So here's a short, brief historical review of quantum mechanics plus how can I get rid of this? So how quantum computer develops. First of all, we have the, let's say, principles of quantum mechanics, and it all goes way 80 years later. We have Dr. Feynman proposed the idea of developing a quantum computer. And then several decades later, some well-known scientists developed some well-known algorithms to show that there is a possibility to achieve quantum advantage. And then we march forward to have the first, let's say, first ion trap quantum computer, which is a prototype model, popped up in 2000. And then from then we have the race began. And you see from 2007, we have a lot of, let's say, real quantum hardware under development. Now it's still an active area, at least for industry. And why quantum computing is, now let's see what is the advancing frontier of the theory and the experiments with the application of quantum computer. Let's say we have theoretical development for a lot of models, and we also have a lot of, let's say, experimental setup. For example, a lot of data we need to analyze. And this all reduces to some math problems like simulating quantum dynamics and the structure, optimization, classification, and the classification of data, regression of fitting stuff, and the various quantum algorithms have been developed to solve those questions. And today we also have, let's say, some world-leading companies, tech companies developing, let's say, fancy quantum hardware like this is IBM, this is ion trap. And quantum computing nowadays sees a cross-fertilization with machine learning, and also it has also, let's say, a possible future with AI. Now, I learned from Dr. Ding Li that a lot of you are not experts in quantum computing. but however, you are very interested in that. Let me introduce you some background knowledge, a very basic example, such that we will be in the same playground. Yeah. So let's imagine we have let's say 2 registers. Each register records a set of qubits. The first register just had one let's say spin, which is either spin up or spin down, and encodes either 0 or 1. And the second register encodes a set of qubits, and then let's say it stores some wave function psi. And let's see how the quantum state stored in these 2 registers can evolve with time, can evolve with this process. First of all, we have the beginning state to be 0 psi stored in A and B. And then after this so-called Hartmann test, we generalize the superposition of the let's say of 0 on 1 for the first register A, and then we do not touch anything on the second register. Then via this action, the controlled U operator, it is controlled on 1, and then we would find out this state controlled on 1. We would act U on this side, and then we again act this side Hartmann gate to the first register to have this state to be this. I mean, just some simple math, and then we have the classical, let's say, measurement. So we can calculate the probability for us to get 1 and the probability for us to get 0 from this measurement. And if you do the math, you will find out that the difference between the probability here gives you the let's say the real part of the expectation value of the unitary U with respect to the input wave function psi. There are also a way to calculate the imaginary part on quantum computer. And in this way, you can get both the real and the imaginary part for the for this expectation. This is just a simple example, which is Hartmann test. And I will also introduce some basic knowledge or strategy to do many-body calculations, which a lot of you are interested in here. If we would like to do some many-body calculations, we would start with a Hamiltonian. It's a kinetic energy plus interaction for a system. And then we will select a basis. We will calculate the Hamiltonian matrix representation in this basis set. And then we will find out a Hamiltonian matrix. By solving the eigenequation, we can get the eigenstate and the corresponding eigenvector. So this is the basic knowledge 101. And here's an example. For example, if we have the single particle basis, these phi 0, phi 1, phi 2, and based on them, we can construct the Fock state. Fock state set like D, F, G, like 0, 1, and 0, 2, 1, 2, 1, 2. And the question is that how can we calculate the Hamiltonian? For example, the following Hamiltonian. Where we have in our knowledge the anti-commutation relation of the fermion operators. Now the question is, for example, let's be realistic and specific. How can we calculate DHF? Now I'm writing down this expression to you, and after some let's say educated guess, we find that only the highlighted this monomial would contribute in this kernel. Now let's work out the math a little bit. So we would like to calculate this kernel, and let's write down the few body matrix element 0.4, and also how B1 acts on D and how B2 acts on F. And we go straightforward. We go in a straightforward manner. And according to the anti-commutation relation, we would collect a few phase in our calculation. And then we would find eventually to be 0.4 a phase times some intermediate state phi 0 single particle basis here. And another state, another anti-commutation relation, a phase, and another intermediate state. And we write them down to find this kernel, which is 0.4 in the end.
Weijie, sorry, are these nucleon creation operators?
That's right.
Okay.
Fermionic operator.
Okay.
Okay, now following the similar procedures, we can calculate the rest elements in this matrix representation. So I believe most of you have been looking through this math procedure, though in different formula or different logic. But the question is, what do we learn from this many-body calculation that could be useful in a quantum analogy? So what do we do special, which would be special to design a Hamiltonian representation, a circuit representation for Hamiltonian is the following. We first need to detect all the Hamiltonian monomials that could contribute. Then we need to test the phase, those -1 to some power, to scale the possible contribution of a certain monomial due to the anti-commutation relation. And then test the occupation of a certain single particle basis to avoid the vanishing cases. And then we need to compare the intermediate state to have the also normality relation here. If this is 0, then everything is over. And then we need to collect all the contributing few body matrix elements, like 0.4, with possible scaling of the phase. We need to collect all of them scaled by a phase. These are the knowledge we learned from the above, let's say, math. Now, this is some graph about how we can construct a quantum circuit. What's the logic of construct a quantum circuit to eventually encode the quantum Hamiltonian? It's just something like we can construct a quantum walk based on the Hamiltonian. Like we can act all the monomials on this initial state. And also we can act all the monomials dagger on the final state. And then we can create a set of let's say a set of intermediate states. And in the end, only a few would connect together according to the phase and according to the few body matrix elements. And in the end, we collect all of them to get the many body matrix element. This is the idea of designing the quantum analogy of computing many-fermion Hamiltonian matrix elements. So, however, we also need to worry about how we are going to encode a many-fermion state in quantum computer. So there are many of them. Some of them are direct, so-called, let's say, direct encoding. Direct encoding does the following. We have a Fock state, for example, from size 0 up to, let's say we have, for example, 6 single particle bases. I would record the occupation of each single particle basis by a specific qubit. That is 1-to-1 mapping. Therefore, the Fock state F, A0, A1, A2, A3, let's say would translate to a binary string, let's say in this system register. And the other qubits I would put there to record the possible, let's say, possible tips, possible lessons we learned from the previous calculation, that we need to detect flag areas to record the validity of the action of the annihilation operations and the flags the areas of the creation operations on certain Fock states. And this zeta, we need it to encode a factor for the due to the anti-commutation relation. Now, this is let's say this is a circuit, half of the circuit that we encode the Hamiltonian matrix element. The many-fermion Hamiltonian. I'll show what it does. It looks complicated at first. Let's say we would first, create a superposition of the indices because we index every Hamiltonian monomial by an index. And then we will test the occupation of the annihilation operators. And then we will test the occupation, and then we will flip those occupations from either from 0 or 1, or 1 to 0. However, some of them are illegal. Therefore, I would like to record those illegal information in this qubit. And then I will do the same thing for the creation operators. And then I will evaluate all the possible phases I need to detect the anti-commutation, how many anti-commutations I have done to calculating the many-body matrix element. In the end, I would encode the few body matrix element in this qubit. It looks complicated, but the idea is fairly straightforward. Let's say when compared to the classical analogy, which I just introduced. You have to believe me in the math. Like if I would like to encode, let's say, the let's say Hamiltonian, which contains all the two-body matrix elements, two-body interactions, or two-body terms, then I can construct the walk state based on the let's say F walk state, and then I can construct another walk state based on the let's say walk state G. Then I just like previously the map, I would collect all the contributions by some manipulation of these walk states. And in the end, this is a key formula, or the right-hand side of this formula is a key that we have the let's say circuit representation of this Hamiltonian. This G and F are random, they are arbitrary. What can we do with this input scheme, the Hamiltonian input scheme? So we have introduced that we have a block encoding of this Hamiltonian. And with this block encoding scheme, we have a very straightforward method to block encode the first kind of Chebyshev polynomial of H prime, which is a T2K, T to the odd, the even order and the odd order by some straightforward manipulation. These are just some circuit, but the idea is that we can encode the Chebyshev polynomial of H prime. And then based on these Chebyshev polynomial, we can construct a set of Krylov bases. And this set of Krylov bases based on a pivot vector which are chosen to be of specific symmetry property, like the magnetic projection, for example, and also the total angular momentum, which would be, let's say, just pick whatever you want. Then based on this Krylov basis, we can evaluate the expectation of the Hamiltonian matrix element and also the let's say overlap function, overlap of these Krylov bases. And they can be written as THT, TT. Via some let's say mass property, we can reduce these matrix elements to some simple expectation values of these Chebyshev polynomial. And this is the key idea, that by quantum computing, we just need to evaluate these the expectation values of these Chebyshev polynomial with respect to the pivot vector that are chosen to be some symmetry properties. Then these are input to the classical computations to construct the generalized eigenvalue equation to get the eigenvalue. The key idea is that we have the quantum computer to take care of the many-body physics here and input to the classical computer to do the rest of the job. Let's say the intuition is that if we can reduce a many-body calculation, the structural calculation of the matrix size of 10 to 12 down to 10 to 3 by this method. Let's say these are some work done before by my supervisor and his collaborators.
So why is it not possible to do this polynomial representation of the Hamiltonian? I don't know how to call it.
Can you
In a
speak
classical
louder,
computer.
actually?
So why is it not possible to do this? If I'm understanding, and maybe I misunderstood something, you're expressing the Hamiltonian as the sum of polynomials, right? And you're doing that on the quantum computer, and then the diagonalization is done on a classical computer. So why is it not possible to do this decomposition of the Hamiltonian into polynomials onto the classical computer? What do you gain? What do you gain to do quantum? This is missing.
So let's imagine, so this part, if we do this on classical computer, we need to take care of the many-body physics, which grows exponentially with the particle number and also the single particle basis. However, we would like to employ the quantum computer. Therefore, this kernel is extremely challenging to evaluate, right?
Dimension-wise.
That's right.
Okay.
Therefore, we ask the quantum computer to do that in a quantum way.
Okay.
Yeah.
But just on that point, so do you have control about which part of the spectrum you want to
Yes.
you want to calculate?
Yes. So by wisely choosing the pivot vector, yeah, I'll show. Maybe we have discussed this in our paper, and for example, if we would like to focus on some specific, let's say magnetic projection, for example, specific n and also specific j, you have a freedom to choose those size 0, such that you would spot.
In terms of energy.
In terms of energy, we are inventing a new quantum algorithm that can do the job. Yes, the answer is yes. So this is just a simple application of our calculation of the calcium isotopes 42, 44, 46. And this is a Hamiltonian, model Hamiltonian. It's a phenomenological, but we would like to demonstrate our calculation. And we do the calculation in 0F7 shell. And we, let's say, develop the matrix representation of this guy and do everything classically. And also, alternatively, we do everything in quantum approach. And our quantum simulator, we employ the IBM Qiskit state vector simulator to do that quantum calculation. And we find our result from the quantum calculation agrees well with the classical theoretical calculation. And both of them, let's say, agrees well with the experimental data. And currently what we are doing is we are improving the Hamiltonian input scheme to get it with a simpler structure. And that is, let's say, easy to handle. And then we are also developing an efficient quantum algorithm for the spectra of the oxygen isotopes, like the, let's say, we target for some specific energy region. Yeah, but you can also discuss with Chen Zhenrong Qian. I mean, his supervisor, Dr. Ding Li, is his fancy work.
But this method is very different from what he's doing.
Yeah. But I'm talking about something else. My focus is on something else. Dr. Ding Li's work is suggesting that if we have a Hamiltonian, the information of Hamiltonian, what can we do to extract the spectrum? But to do that calculation, we need the input of the Hamiltonian first. Our work is doing that part, that we would like to know how can we input the Hamiltonian to a quantum system. And such that Dr. Ding Li's knowledge could work eventually to get a spectrum. Yeah. That's one way to think. Yeah.
So if I understand you correctly, so your algorithm, your mapping will get the many-body matrix elements, right? For the Hamiltonian.
Yes and no. Yes and no. We have a general Hamiltonian. The second quantized Hamiltonian. For example, the second quantized Hamiltonian written in the circuit representation, and by whichever, let's say, state, either a pure, let's say, either a pure configuration, many-body configuration, or let's say a superposition of these many-body configuration, we can always produce the matrix element for that. But quantum computing, let's say, does things in, let's say, if we find out a possible eigensolver, we do not need to worry about that level of problems. Let's say, it's just the information of Hamiltonian. And given the inputs, given some design of the, let's say, pivot vector, you will get all the eigensolver, all the way down to the result of the eigensolver.
Yeah. So I understand that you are going to get the many-body matrix element from your
expectation values from quantum computing. Yeah. And then these are, let's say, then we collect these expectations, right? And reconstruct them according to these relations, like H1 prime is equal to something, omega ij is equal to something. They're all written in the expectation values, right? Therefore, we will put the generalized eigenvalue equation constructed.
Okay. I understand.
Yeah, sure. Yeah. Thank you. Question?
I'll ask later. It's all good.
Sure. Okay.
I actually have a question. When you calculated these results on this slide and the next slide. Were you doing these on qubits on like non-erring qubits, or did you implement or did you simulate these on qubits with errors and then implement error correction?
No, we do this on the let's say IBM quantum state vector simulator. We do not. I mean, surely there is a freedom to play around with those error mitigation, introduce the error rate for those qubits, for example. Yeah, and for this design, we would like to be a little bit hand waving because the circuit is quite nasty at the moment.
Gotcha.
But with the improved design, we would stand a chance to study the error and to error rate, how they propagate along this circuit, let's say.
Awesome, exciting. Thank you.
And I hope I'm still on time. And the second part is now we have the fermion, and which is bright. We need to also have the groom, which is the bosons. How can we do the counterpart of and together they will make the simulation or calculation of a whole bunch of let's say physical process, let's say available, like the absorption or emission of certain bosons, for example, in the fermion line, for example. So now I would like to introduce some stats still from 101. We would like to calculate let's say this A stands for the boson operator. We would like to calculate the many-body matrix element for this Hamiltonian. Like this is a Hamiltonian, and I have a single boson mode to K, where K, for example, it can be 1, 2, 3, 4. And the many-body state can be is a little bit, let's say, complicated than the many-boson state, because we need to construct the, let's say, proper normalization of this many-boson state. And also we need to consider the commutation relations of these boson operators. And in the end, we also need to consider the action of the boson operators on those many-boson state, and with proper scaling of the according to the normalization factor. Now the question is that if we have this many-body state to be mode 2 occupation 1, mode 1 occupation 2, if we have this many-body state, what would be the many-body matrix element for this edge? So now this calculation is still analogous to the fermion case, that we need to collect all the contributions from the responsive monomials. Like we do not want to collect anything that is relevant to mode 3, because nothing is going to be there. And now we let's say calculate all the possible contributions from these monomials to be this is a few body matrix element, which is 1, and this square root 2 starts from, let's say is from the let's say action of the boson operator to the many-body state according to its occupation, and these are the scaling factors. And in the end, we would also see the orthonormality of the intermediate state, which is 1 here, fortunately, and this in the end we get 2, and we can run the similar calculations again, few body matrix element scaling according to the according to the occupation, and the overlap of the inner product of the, let's say, intermediate state. And then in the end, we would let's say we would sum them over to get the many-body matrix element. So this is again 101. And now, what do we learn from this calculation? Again, what are the steps to compute the Hamiltonian matrix element that would be useful for the quantum representation or circuit representation for Hamiltonian? Lesson 1 is we need to detect all the, let's say, Hamiltonian monomial that contribute, provided the Fock state, for example, Fock state. And then we also need to test the occupation of those active nodes, because some does not contribute. Then we need to check the orthonormality of the intermediate states after these actions of the monomials. combination of boson operators. Then we also need to collect all the few body matrix elements with their respective scalings according to the occupations on those modes. And in the end, we get a sum. These are the lessons and tips we need to keep in mind when we are designing the quantum analogy. So again, I'm drawing this graph to show that how, let's say, how a certain Hamiltonian could act on, let's say, many boson states. And in the end, it produces some intermediate states with possible scalings of the according to the occupation, and also the intermediate state, and also the overlap of intermediate states. And in the end, these states projected together to find what is the real contribution here. That is how we see we need to construct a network and map to another network with possible scalings of the factors and view body matrix elements.
Just a quick question on this plot. When you're choosing your arrows, do you have a color coding in mind? Like why some are blue and some are red?
Yeah.
I don't see why.
Some of them are contributing stuff. Some of them are not contributing stuff because the annihilation.
Okay. Thank you. Yeah. And so the one contributing here, the blue one, I'm guessing.
Yeah, something like that. There are some tricky part here. Yeah. Yes, I agree with you. The third one is a contributing stuff here. Yeah, but just I'm trying to convey the idea how we are trying to build a network according to Hamiltonian, and in the end, they successively project to the final state, and those final states reveals this part. That is the projection over the something. And those red and black arrows stands the few body stands for has a scaling of the few body matrix element, and also the scalings of the let's say scalings according to the occupation of the node. So I mean, we also need to discuss about the how to encode the boson mode. Boson Fock state. We employ so-called direct encoding plus compact encoding scheme. So I do not. If you ask me what encoding scheme is, I would say that is a summation. So the idea is the following: we would let's say employ a circuit, a set of qubits to encode the occupation of the mode. For example, this register, the line stands for the qubit, and we would recruit a set of qubits to form a register K, and that register K stores the occupational mode Q in binaries. That means if we have a K, mode K with 7 occupation, we would have 11110 here. That is, we are storing everything, the occupation in binaries. And because we also need to scale the single few body matrix elements according to the respective normalization of the boson operators acting on mode K, we would recruit another qubit, just a single qubit register to record that information. And then we also have some similar stuff for system M, and also a register to record the normalization factors for mode M. And for example, M to the 5th power, we have 101. So we have a logarithm of the modes, let's say, when we are considering how many qubits we need. And the example is that if we would, this example is able to encode, let's say, 2 power 4 times 2 power 3 different, let's say, many-boson states. It is super powerful if you scale that up and simultaneously. Now, to encode such a boson Hamiltonian, we need to let's say do some extra manipulations of those boson operators. We need to we need to squeeze the boson operators according to their total occupation lambda k, and then these squeezing factors will be absorbed by the few body matrix elements like BJ0 and BJ1 stuff like that, and then in the end, we have some other, so we have an equivalent Hamiltonian. However, all the boson operators are properly squeezed. Now, we also need to collect all the contributions for the possible boson combinations of boson operators. For example, like this WK stands for like single boson operator, double boson operators, triple boson operators, and triple annihilation, double annihilation, triple annihilation, and some possible combination. And we designed the circuit module for each of the combinations. And there are, upon these actions, we would collect, let's say, some factors according to the normalization factors, which is inherited from the action of the boson operators on many boson state. And then I also count how many different occupations, what is the change of the occupations? Like if we have a B dagger, I will have the occupation to be +1. Triple dagger, I will +2, +3, -1, -2, -3, 0, 0, something like that. So this is a simple circuit, let's say, representation for a boson operator WK, and it acts on the quantum registers, which first stores the modes, occupations of a specific mode K in the system register K, and another register to store the scaled normalization factors. And yeah, this is a very interesting, let's say, gadget I would like to introduce to you, which is so-called quantum subtraction. Like each line stands for a qubit, and this circuit can represent a number from represent the integers from 0 to 7, and this circuit does the subtraction in parallel. That is, it just reduces every input number to be -1, and it's very interesting to see everything in parallel. And if you have 0, you will immediately hit to 7. That is a round loop, something cyclic. If you would like to say it's a cyclic group.
4 minutes.
4 minutes. Okay. And these are the circuit representations for a sample many-boson Hamiltonian. And then let's say again we write everything down according to the mass, and in the end we block encode this Hamiltonian. Let's say according to our work state design. And again, this Hamiltonian will be input to the so-called Kirchhoff subspace, that quantum Kirchhoff subspace diagonalization approach to get some spectra. For example, here we show how this guy works, how this approach works for the 1 + 1 d⁵ theory, and we get the Lagrangian, and we obtain the lifelong Hamiltonian with the approach of discretized. A discrete light cone quantization, and we get the specific form of each piece of the Hamiltonian monomials. And for example, if we restrict to the total momentum k equal to 4, it's a model space, we can get the following many-body states. The red color coding stands for the even particle sector, and the blue stands for the odd particle sector. And we find out the Hamiltonian with proper squeezing. We, let's say, have different modules which will be necessary for each part of the monomials, and we label them with indices like zeros term, first term, second term, third term, so on, so forth. So these are parameters for the circuit design of the boson operators for each monomials. And in the end, if we do the classical calculations, just like the one I introduced you a few minutes before, we can get the Hamiltonian representation. It is block diagonalized because the ⁵ theory is has a very interesting property, like it will preserve the number of particles. Therefore, you will see the odd sector does not talk to the even sector. And in the end, we have, let's say, alternatively, we encode the many-boson Hamiltonian via our input scheme, and we employ let's say the eigensolver I just introduced you to the symmetry adapted quantum Priloff subspace method, and we employ the IBM Cascade quantum simulator, a state vector simulator, to get the ground state of the even sector to be 0.9, and the out sector is something. And this is enable you to the 524 theory enables you to study the spontaneous symmetry breaking stuff, and these values agrees with the exact results by direct matrix diagonalization. And also, let's say with this input model, we can do also dynamics simulations. The dynamic simulation relies on the gadget of this so-called time evolution unitary for either time independent or time dependent Hamiltonian. And with this input model, we can let's say construct such a unitary. And we are doing this job these days in our upcoming project, in our ongoing project to do that. And a few very insightful and efficient dynamic simulation algorithms are, if you are interested, that would be quantum eigenvalue transformation, quantum singular value transformation, quantum signal processing for simulating time-independent Hamiltonian, and rescaled Dyson series for simulating time-dependent Hamiltonian. And this, the last thing, is able to calculate the so-called path integral. And I mean, surely there are a lot of rooms for all of these algorithms. So there's still, we have a lot of work to do. And people are also introducing interesting algorithms and novel applications these days. Summary, and nuclear many-body calculations, nuclear many-body problems are computationally challenged for classical computers. And however, let's say quantum computer might be a promising candidate to solve these problems with efficiency. In this talk, we introduce Hamiltonian input schemes for many-boson and many-fermion systems. And based on these Hamiltonian input schemes, we can calculate the dynamics and the structure utilizing quantum computers. In the next step, we plan to improve the circuit model, the input model, and would like to develop efficient algorithms for ab initio quantum many-body structure and dynamics calculation on near term and the future quantum hardware. Stay tuned. And thank you. If I would have some extra time, I would like to introduce something which is relevant to Dr. Ding's work, which we utilize that to calculate the spectrum. And in the end, we analyze from those spectrum, we managed to calculate the scattering phase shift, let's say, of many-body systems. And also, we are also introducing some quantum algorithms to simulate some QCD dynamics later on. But both of them would see the benefit from the input model later on for interesting applications. Indeed, the QCD dynamics would have to also see some interesting jet physics problems. Yeah, that will be all. That will be the final of my talk. Thank you very much.
Okay, thank you for this excellent talk. Are there any questions in the audience?
So I have a question. At some point you were showing a spectrum and you were writing experiment theory. You were showing a spectrum for a simple and Hamiltonian that had like pairing, or you were showing like levels 0 plus 2 plus etc. And you had the experiments versus theory. So what is theory in this case? Is this the theory you obtain with your quantum calculation of the Hamiltonian? I'm not sure how to put it.
You mean this?
Yes.
Okay.
So experiment is, what is experiment? Experiment is what is measured in the lab, or what do you call experiment?
Measured in the lab, yes.
Okay.
So this red color coding red is experimental data for those lower lying spectra.
Okay, and so then you compare with your calculation in black.
That's right.
But so the calculation that you've done was this hybrid quantum classical computer. And if you do everything on a classical computer, you obtain the same black lines.
That's right.
Okay.
And the fancy part is this. I'm really excited to post this work before the end of the year. So that enables us to calculate the oxygen isotopes, the low-lying spectral of oxygen isotopes.
What is the dimensionality of the problem
For what?
for these systems?
For this system? I have not yet counted those dimensionalities yet, but the idea is that, I mean, quantum computing, it does not, I mean, based on my point of view, it does not care about the matrix dimension. It cares about how you input those data in the quantum circuit made by the matrix elements. Like for here, I have the these are calculated by me. The two-body interactions. The two-body interactions based on effective field theory and the SD shell in the SD shell. So total of them will be let's say somewhere around 180. But this shows you the logic of the work. Gradually, we start from the previous prototype work, where the dimension here is 64 by 64 in matrix elements, few body matrix elements. And gradually we have 180. Let's say this is a more complicated problems, but we have a very interesting quantum algorithm to introduce to society. And later on, it will be a full blossom ab initio many-body problem, like the one I introduced here. Like for carbon-12, if you can see carbon-12 here, we have 80 single particle bases, two times 40 for proton and 40 neutron. And the matrix, few body matrix element is a few copies of 22308 according to 3J symbols, 6J symbols of that. And in the end, that will be a full blossom stuff that would hopefully exceed the classical computation.
So how do the complexity of the circuit scale with?
So that's I didn't introduce this concept here, but the complexity is let's say well considered in this work. We have the worst case of the calculation that is maybe 1,000 times something around 1,000 times number of single particle bases for fixed power, without any approximation, without any restrictions of the symmetries. You see, not all of the few body matrix single particle bases can join. Therefore, that will see a significant reduction. Yeah. Number of, if you would like to take the number, that is a number of single particle bases to the fifth power for the Hamiltonian with two body interactions at most. So that would be a surface depth.
You had so when you use that Q.Q schematic interaction, right? You had those calculations with the quantum simulator, and you compare to I forget, is it slide 18 maybe? No, you have the Q.Q. Yeah, this. So this red ones are your calculations with the simulator, right?
Blue ones are so the black ones are calculations.
Oh, the black.
Yeah.
And what are the red ones then?
Experiment.
And do you compare? So what I'm wondering is, you couldn't use this on a classical computer, right? Like you didn't have to do with the Q.Q. So is there any difference from the classical computer in this case?
No difference.
Because you didn't use any noise.
Yes.
That's why you don't expect.
And the other aspect I would like to point it out is that the development of quantum hardware is still at the initial beginning stage.
Yeah.
Therefore, let's say we have not yet got the power to produce any quantum computer that would be beyond the power of let's say realistic supercomputer in this nation.
Sure. Yeah.
Therefore, all of them are demonstration calculations, and we would like to add up.
Okay. That's good. Any more questions? Yes, please.
On the previous slide, you have the pivot. Could you talk a little more about how you choose that? You said like if you make a wise choice, you can specify what energy range
Oh, energy range. I would like to introduce the energy range. This is a commercial secret yet, but let's say we have an algorithm to tune the energy range. Yes, but for example, if your question is asking how we can wisely choose a pivot vector with some certain symmetry, I would like to first of all refer you to this work. First of all, second of all, I would briefly introduce how we manipulate the J labels of the subspace. The idea is that according to the M, if you are familiar with that M scheme, if you recruit the M scheme with a certain projection like -2, or +2 or -2, for example, then this subspace has no support for J equal to 0 and J equal to 1, let's say, levels. Therefore, in that way, if we produce, up until now, everything is in the occupation level. Therefore, we have a direct control on which state is occupied. For example, if we have this Mj, if we would like to have the Mj equal to +2, we can recruit +7 and -5 state, for example. We will neglect the states like +7, -7 states for a two-body system. Therefore, we can have a specific control over the total Mj, and hence we will have the control to rule out the unnecessary J state.
Okay, but if there's like some sort of intruder state, can you still account for that in, like if you have I don't know, maybe in the construction of the Hamiltonian, is there still a way for you to account for like states that might have some sort of strange behavior, or is that just like a necessary truncation?
I'm not sure about that. I understand your question. I'm not sure how weird I can be.
Yeah. Okay.
But surely we are human, we are creative. Therefore.
Got it. Thank you.
So, about the Hamiltonian, do you think if you have a more complicated operators, for example, tensor force or three-body force, that will introduce some significant difficulty in your mapping, in your algorithm, or it's just a smooth, you need introduce more? No, I think you will use the same number of the circuit, right? But with more operators, right?
More operations, yes. Yeah. But the idea is that to include three-body force, that is a significant difference between quantum chemistry. Well, the Coulomb force is two-body forces, for example, in quantum chemistry. It is, and if you include in ab initio classical many-body calculations, if you include the three-body force and the higher order force, for example, you would see a significant increase in the number of few-body matrix elements, right? And the matrix will be a lot denser, such that the current sparse matrix based, let's say, Lensher's algorithm, sparse matrix based, let's say, matrix diagonalization stuff cannot do. Therefore, let's say we can resort. This is indeed the very necessity we see that could be complicated, such that the sparse matrix algorithm does not work. We have to go to some other scheme. Did I answer your question?
Okay, we're almost out of time, so let's thank Weijie again.
Yeah, Max.